Given approximately optimal demonstrations of a multi-stage task, our method seeks to find a parametric linear temporal logic formula consistent with the demonstrations. To do so, our method relies on an iterative falsification loop. That is, we propose candidate parameters theta hat s and theta hat p for the LTL formula, and check if there exists some lower cost trajectory that satisfies the candidate formula. If there isn't, the candidate formula is consistent with the demonstrations, and we terminate. Otherwise, the candidate formula is inconsistent with the approximate optimality assumption, and we return to propose another candidate formula which does not accept the generated counterexample. This process repeats until no counterexamples can be found. Then, the learned LTL formula can be used to plan new trajectories completing the task. In this example, a point robot is tasked to first grab a mug, bring it to a coffee machine, and then deliver it to a goal, all while avoiding obstacles. This task can be encoded with the LTL formula phi of theta hat s. We get two demonstrations of this task, where the atomic propositions differ, but the task structure remains identical. To learn the task structure, we employ our falsification loop, generating this counterexample trajectory. At the next iteration, our loop terminates, and we can use the return formula to plan this new trajectory. In this example, a simulated 7DOF arm is tasked to fill a mug, grasp the mug, and then deliver it to a goal region while keeping the end effector upright after the filled mug is grasped. We obtain two demonstrations completing this task, which can be enforced with the following LTL formula. We again apply our falsification loop, generating two counterexamples for candidate LTL formulas before the method terminates with the correct formula. We can then use the learned formula to plan new trajectories completing the task starting from different initial conditions. For a class of tasks where subtask ordering is not important, we can leverage the spec optimality condition to learn a consistent formula in one shot without using the falsification loop. Please see the paper for more specifics on spec optimality. In this example, a 12D simulated quadrotor is tasked to visit the three green regions in any order while not crashing into the building. We obtain 4 demonstrations completing this task. Using the aforementioned spec optimality based solution returns this consistent formula in a single shot. We can then use the learned formula to plan new formula satisfying behavior. To demonstrate that our method scales to the challenges of real hardware, we learned a multi-stage tabletop manipulation task on a real 7DOF arm. The structure of our method remains the same, but the planning and execution phase will differ. The atomic propositions in this case will be related to the manipulable objects in the scene, which we will sense with the Kinect. The sensed APs and the learned LTL formula will together be used to plan a trajectory, which will then be executed in the real-world environment. In a Unity VR environment, we record a single demonstration of the task. The task is to grasp the tomato soup, place it in the movable blue box, and deliver the loaded box to the blue delivery region. While the box and soup are both grasped, the end effector must remain upright to avoid spills. Then, the arm must grasp the Cheez-It box and deliver it to the green region. All these objects come from the YCB dataset. We employ the falsification loop to learn the LTL formulas. Here are various counterexamples which are generated, all of which lead to lower costs due to missing constraints like ordering the tasks incorrectly or failing to deliver the correct objects to the correct locations. We feed the RGBD data from the Connect into a neural network-based object segmentation framework, which returns a segmented image and segmented point cloud. We run ICP on the segmented point cloud with 1000 random initializations to estimate the object poses. Note that the recovered poses are imperfect due to occlusions and sensor noise. However, this level of accuracy is sufficient to complete our task. We use this OpenRave scene of the real environment with the estimated object poses to plan a new trajectory. Finally, we execute the trajectory and obtain this execution on the physical robot.